I want to double check, or excuse me, I do want to welcome you to exponential and log equations. So we get to take all that you've been learning and we're going to put it into something that looks simple and actually is going to be fairly simple. So our goal today is to solve exponential and logarithmic equations. So I'm going to show you a couple different skills to do. The key thing is just to remember what the definition is. And at times we'll use it, other times we won't. But your calculator will come in handy, so make sure you have it. So let's take a gander at A here. The first thing that I noticed about this particular problem, not every problem I'm going to see, but this particular problem, I can take this 16 and I can rewrite it in terms of a 2. I notice it. That's just something I've noticed. Now, if you didn't notice it, that's okay. You don't have to do it this way. We'll show you other ways to do this. But I noticed that the 16 can be rewritten. So notice the 2 to the 2x I'm going to keep the same. But what does 16 equal? It's 2 to the 1, 2, 3, 4th. Is that right? 2 to the 4th. So I'm just going to rewrite that. 2 to the 4th. Now, let's recollect. Now that we've got it here, such that I have the same base, if I had given you a problem that looked like this, you don't have to write this. 1/2 equals x over 2. Many of us will just jump in and start cross-multiplying and try to solve it. But for those who are aware, we say, oh, look, the 2's are the same, so what must be true about the numerators? They must be the same. Well, lo mismo aquí. Since the bases are the same, what must be true about the equations? Or excuse me, the exponents. They have to be the same too, yeah? So that means 2x is equal to 4. I'm just ignoring the base entirely. And x is equal to 2. And we all say, word to your grandmother. So let me go ahead and just check that real quick. Again, the checking is something you should do always and forever, always and forever. We met in a chat room, and now our love can fully bloom. Always and forever, always and forever. Hey, it worked. Great. As we attack this next problem, notice what I see about the 27 and the 9. Neither one of them can be rewritten in terms of the other as a base. Oh, but can I say 9 times 3? You can, but that's not the same base. 9 times 3 are two separate. So here's what I'm going to do. I'm going to take the 27 and rewrite that in terms of a 3. And then I'm going to take the 9 and rewrite that in terms of a 3. So instead of making one become the other, I just went ahead and took both bases and converted them to a common base. Again, if this is hard to see, you don't have to do this method. We'll show you another method later where you can rearrange things here. All right, so now let me finish it up. Our exponent property here says if I have a power of a power, I need to multiply the exponents. So 3 to the 6x equals 3 to the 2x plus 4. Don't forget that this 2 has to multiply the x and the 2. Distributive. Now, since the bases are the same there, we can equate the exponents. So 6x equals 2x plus 4. 4x equals 4, and nicely, x equals 1. A check for that is just plugging things in. 27 to the 2 equals 27, excuse me, not 27, but 9. 9 to the 3. 729 here equals 729 here. And there we go. So let's commit to the answer. X is 1. Check works out. So now here's another method to solve things. Notice this one is a little bit more complex. Why? Because the 21 cannot be written as a base of 4 easily. It can be, but the exponent is so complex, I just don't know. So watch the magic here. If I take the log of both sides, or I can rewrite it as a log. So remember, I take the log of this number, so excuse me, this is my base, 4, and then this here is the big number, so log 4 equals x. And there we go. Now, in a previous problem, or excuse me, previous work, we did change of base right here. So I'm going to go ahead and write that out over here so that you can remember. Change of base. So, log of 21 over the log of 4. So change of base says take the bigger number, put it on top, put the itty bitty one, put it on the bottom, and notice the logs here are 10. So it's a common log, we don't have to write the 10 there. Now we plug this thing into our handy dandy calculator to get an approximate value. It's safe to round it to the thousandths or something like that. So here we go. Now let's just pause. Remember what this is asking me. If I take 4 and I raise it to this power, I should get 21. So that's easily checkable just using it on a calculator. 4 to the 2.196 should be approximately 21. So again, I can just check that. So let's take a gander at a problem like this. Before we logify, remember, we always need to inverse things because we want to isolate the thing that we are undoing. So I'm going to isolate the 4 to the x power. So 4x is going to give me 25. Whoopsie daisy. 4 to the x is equal to 25. And then we're going to rewrite it using this base here. Log 4 of 25, log 4 of 25 equals x. Now I can plug this handy-dandy thing into my calculator after I use the change of base, log of 25 over log of 4 to get an approximate value. 2.322. Remember to ask the question, when I take 4 and raise it to this power, the 2.332, I should get 25. And when I subtract 5, I should get 20. So let's come back together. We are going to exponentiate both sides, or another way to say that is to rewrite into exponent. Previously, we rewrote into log. So this one here, if you recall, it's 3 to the third power, so that goes here, is equal to this right here, the 2x plus 3. So notice in rewriting it in exponent form, exponential form, I now have the variable isolatable fairly quickly. So the left side here becomes 27. The right side stays the same. I'm going to subtract 3 from both sides. And then my final answer is 12. To check that, put 12 here. And 12 here gives me 24, 27. And then when you calculate this, log 3 using change of base, you do indeed get 3.